Good evening, everyone, and welcome to today's program, Mapping the Origins of the Universe, with prominent researchers from the National Science Foundation funded telescopes in both the South Pole and Chile. We'd like to thank the University of Chicago's Department of Astronomy and Astrophysics, as well as the teams at CMB S4 and SPT for partnering with us to make this event happen. C2ST, the Chicago Council on Science and Technology, is an organization that was started in 2007 with the mission to help the public understand and appreciate science and technology. We do approximately 30 programs a year that are free or low cost. And if you'd like to learn more, you can go to our website. And if you would like to donate to support programs like this in the future, you can also go to the website. And if you like what you see and hear, please consider joining our mailing list so that we can keep you in touch with the happenings. So in tonight's program, you are able to ask questions of the scientist. And if you would like to do so, you can type in c2st.cnf.io into the browser at any time, and we will be able to review your questions and share them with the presenters. If you would like to ask questions on Facebook or YouTube, staff from Chicago Council on Science and Technology will retrieve those questions and share them with us as well. So let's get on to this really exciting program and all these amazing speakers we have joining us today. We're going to have a format where we have several of the presenters give us some background on the programs that they are involved in, have a little bit of time for question and answer. And if we're very lucky, we will be connecting to some special guest in the South Pole. Our first researcher that will be speaking this evening is Dr. Joe Dunkley. And Joe is a professor of physics and astronomy of astrological sciences at Princeton University, and she researches cosmology and studies the origins of the universe and the evolution of the universe. Her major projects are at the Atacama Cosmology Telescope in Chile and the Simmons Observatory. We're also lucky to have Alysha Shugart with us this evening, and she's the newest and first observation specialist at the Vera C. Rubin Observatory in Chile. And before joining the Rubin team, she served at the Gemini South International Observatory as a science operations specialist, and she's also a diversity advocate for the Aura Centers in Chile. We also have Dr. Bradford Benson, who is a scientist with Fermi, an associate professor at the Department of Astronomy and Astrophysics at the University of Chicago, and a senior member of the Kavli Institute for Cosmological Physics. We also have Cyndia Yu, who is a PhD student at Stanford studying physics, and right now she is working on building new tools to study astroparticle physics, what's happening with astroparticles in the universe. As a bonus, when we have an opportunity, we're hoping to connect with Sasha Rollin and Matthew Young, who are at the South Pole. That will come a little later in our program. But to begin things and to kind of help set the stage, if you will, of why do we study the origins of the universe, I'd like to introduce Dr. Joe Dunkley. Joe, thank you for joining us today.
Thank you so much. Thanks for having me. Okay, I'm going to play my slides. If you can see them. So yeah, it's a pleasure to be here talking about my favorite topic. So, you know, we live in this enormous, magnificent universe, and one thing that's incredible is actually how much we do know about it. We know an enormous amount about this place we live in, this home we live in, but we're full of questions that we just don't know the answer to yet. That we're desperate to find the answers to. And what are some of those? So, you know, we want to know, did the universe we live in, did it have a beginning? Did it have a beginning, and how did it happen? How did we come to be here? What is the eventual fate of space far in the future? What is the future of this place we live in? And what makes up the universe? What's out there? What, you know, which is a little part of it, but what's the bigger thing out there? What's it made of? And are there do we really know all the laws of physics that describe how everything works? Are there things beyond what we already know that we can learn about that tell us how the nature of how true nature works? So thinking about what you'll hear today are some of the ways that we're trying to probe some of these questions. But I want to give a little reminder of what it is we do know and where some of these big questions fit in. So here we are. We live in our little solar system here on Earth, in our solar system, where we look up in the night sky and we see the beautiful stars around us. And the stars that we see are all part of our Milky Way galaxy. And if we're really lucky on a clear night, we might see this band of stars in the sky that you see there, which is the disk of stars of this gathering, this grouping of stars that we live in our Milky Way. And it's a huge place, our own galaxy. We're living inside it, so we can't actually see from the outside, but we are, we have these marvelous pictures of other galaxies beyond our own. This is a little example of one here. A picture of a distant galaxy far beyond our own, but that sort of looks perhaps a little bit similar to what our own Milky Way galaxy could look at. So what are we seeing here? This is a huge spiral of stars. The bright lights you see are stars spiraling into a central core. And it's this enormous disk, and the scale of it really is vast. It's a thing that's light itself, which is the fastest thing we know, takes about 100,000 years to travel from side to side of a galaxy like this, and a galaxy like our Milky Way. It takes only 1 second for the light to get from the moon to us, and about 8 minutes to get from the sun to us. So 100,000 years of light, the fastest thing there is traveling, makes this thing a really vast place. And we've known for about 100 years that we live in one of these galaxies like this, that ours is the Milky Way, and that we now know from using our telescopes that looking out beyond, we see many galaxies beyond our own, like this one and many more. And we now know that space is just full of them. And so this is another beautiful snapshot taken with a big telescope of what's called a cluster of galaxies, where if we take a step back, we see that galaxies group together in these big clusterings together like this, where every spot of light you see is an entire galaxy. Each of those, and each galaxy contains about 100 billion stars. So our little sun is just one of the stars within this huge grouping of stars within the galaxy. And so if we look out with our telescopes, we do see space just littered with these beautiful, bright groupings of stars in these galaxies and in these clusters of galaxies. If we take a step back even further, this is an image taken by the Hubble Space Telescope of just a little patch of sky where if you didn't have a strong telescope, you'd think you were just looking at the darkness, there was nothing there. But if you stare hard enough, you see this little snapshot where every single speck of light here is an entire galaxy itself full of billions and billions of stars. Just if we look far enough and we kind of capture what we know of the observable universe, the space around us, we think we can account for about, we think there are about 1 trillion galaxies in it, each with roughly 100 billion stars. And it's kind of remarkable that we're able to see so far because we have these remarkable telescopes that have really increased in technological prowess over the last tens of years. But so we look out there and we see this, there's a lot of things that we can see, and a lot of things we sort of think we've pieced together through our observations. But we get left with these, despite the things that we think we can understand, we get left with these really big questions that we're grappling with, to do with the contents of the universe and the beginning of it. So it turns out there's a really interesting question, which is, the things that we can see, the stars in the galaxies, are only a very small part of what's out there. It turns out that there's a whole lot of the universe out there that is completely invisible. The stars we can see, but it turns out that there's about 5 times more mass out there that is completely invisible. We think it surrounds the galaxies, it spreads through them, it kind of connects them up. It's here in our solar system, and we call it dark matter. And that's really a way of saying that it's something we don't know what it is. it's something that kind of feels gravity. It pulls clumps together, but we don't know what it's made of, whether it's a new particle, whether it's something that we haven't really accounted for yet. So we're trying to understand what this invisible part of the universe is. And then at the same time, if we look back at these galaxies all around us, we've come to know in the last 100 years, and increasingly in the last more recently, that those galaxies haven't always been there. You know, the beautiful space that surrounds us now has not always been there. And the clue we had to it is that if we observe all those galaxies around us, they all appear to be moving away from us. And that's consistent with us living in a space that is growing and growing and growing. It's sort of stretching in all directions. And the galaxies, as like little markers in that growing space, are all just gradually moving apart from each other. And if we wind time backwards, you come back to a time deep in the past when space began to grow, when it all began to, when the space that we know now emerged. And back then there were no galaxies, there weren't even stars yet. There was nothing that we recognize around us would have been there. We think if we could wind time backwards, we get to a time 14 billion years ago when we just had tiny particles all condensed in a very hot squeeze state that we now call the Big Bang. And we think we can sort of trace pretty well what's happened pretty well over this 14 billion year history, but we don't know what began that growth. We don't know what started the growth of space and started the growth of space that could then later produce this beautiful space full of galaxies now. So it's one of the things we're trying to figure out. And then this other curiosity has shown up lately, which is that space seems to be growing faster and faster, and nothing we really understand about the nature of space could actually make that happen. The possible answers to it are something that we often call dark energy, but it's also another way of saying something that we don't really understand. So there are these mysteries that are fascinating to us, and the wonderful thing about having these questions now, today, is we have these wonderful telescopes available to us, either currently or that we're building, that can let us go and answer some of these questions. Because what you can do as an astronomer is you can look out in space, and actually if you gather light that's been traveling for a really long time, for years and years and millions and then billions of years, you get to look back in time. You get to look back in time by gathering light that set off a long time ago from places far, far away. And you can actually look back all the way to the beginning, almost to the beginning. And then you can look back and see how these galaxies have developed over the universe. And so I've just given you two pictures here, two images of telescopes that you're going to hear about in the following talks, at these incredible observing sites in the world. The first on the left is the Rubin Observatory, being built in Chile. And on the right, you see the South Pole telescope at the South Pole that we'll hear a lot more about later. And these locations are just marvelous observing locations where we've determined are just the best place to go on Earth to go and look at the night skies, or even the daytime skies, because some of these telescopes look at different kinds of light than the light that we can see with our eyes. It turns out that if we want to see things from very far away, that sometimes looking in different wavelengths can help, and I think you'll hear more about that. I'll just finish with an image of the telescope that I use to try and answer some of these questions. It's a telescope called the Atacama Cosmology Telescope. It's pictured here. There's a picture of me 10 years ago up on a mountain nearby it, with it behind me. And the picture you see of this little telescope in the corner is the one that I use. And it's up at 5,000 meters in the Atacama Desert in Chile, where the air is so dry that you get a really clear view of the skies above. And we're trying to gather light from almost the beginning of the universe. It's a sort of sister telescope to the South Pole telescope that you'll hear about some more later. But it's something that it's a wonderful place, magical place, and it's also letting us do magical science. So I will stop there, and I'm going to hand over to Alysha.
Hi, everybody. I'm just going to share my slides. Okay, well, my name is Alysha Shugart, and I am an observation specialist at the Vera C. Rubin Observatory, which is coincidentally the first US-based observatory named after a woman. Vera Rubin here, pictured in the center of my slide, measured galaxy masses and discovered strong evidence for dark matter, which you heard about recently from Dr. Dunkley. This telescope is currently under construction. A recent photo of it is shown in the top right of the slide. I took that photo about a month ago. Now this telescope is being built, and it's for the next 10 years, once it's finished, will have one distinct purpose. And its purpose will be to take the most complete survey of the southern hemisphere sky of all time. The instrument with which it will be able to do that, the Legacy Survey of Space and Time camera, is 3.2 billion pixels large. Each image that it takes of the sky will be 6 gigabytes in size. Every night we will take 10 terabytes of data. Okay, so this is going to be a groundbreaking survey. So what I want to talk a little more about is this telescope, how this telescope is different. Why weren't other telescopes built to do this? Well, I have an example on the left-hand side of the slide. Most telescopes, and there are several large ones of similar size, literally right next door to me. These big telescopes that are 8 meters in diameter, our own Rubin Observatory will have a reflective mirror of 8.4 meters in diameter. Well, these big telescopes typically have small fields of view. So what you'd normally see with one of those large telescopes might concentrate on the red area highlighted of the moon. Now, in comparison, the Vera Rubin Observatory will have an eye that can encompass the field of view shown on the right of the slide. So just comparing those two images visually, you can see a sense of scale and how many different things can be imaged simultaneously by this telescope. So what are some of the goals of this telescope? What are some of the goals of these 10-year surveys? So, you know, this program is related a lot to cosmology. This telescope, just by creating a full and complete picture of the southern sky, will be able to characterize a lot of things that we study just individually, such as expansion and galaxy clustering. We'll actually be able to look at deep scale structures and understand the effects, some of the effects that dark energy and dark matter have on these structures. We'll also be looking locally and do a lot of solar system science, which means identifying a lot more asteroids and things that are kind of living in our local neighborhood. We hope to learn a lot about our own Milky Way as well, and the history of its possible collisions and how it evolved to become the galaxy it is today. Also, another exciting thing about the Rubin Observatory is because we're looking at the sky and we're taking photos of the entire sky over a 3 to 5 night period, we'll get to see how things change in real time on a very quick scale. So it's anticipated that Rubin is going to make a lot of quick real-time discoveries. And what's going to be amazing about that is that once those discoveries are pinged, once those flashes of light, either exploding supernova or the tidal disruption event that the LIGO Gravitational Wave Observatory detected, we hope that Rubin will see those events as well, and that we'll be able to develop a system of cooperation with telescopes that are next door, including the Gemini South Telescope and the SOAR telescope, a 4-meter, which is on the same summit that I am right now, Sarah Pachon. We hope to create this new wave of collaborative and collective astronomy. So when Rubin gets these notifications, when Rubin sees these things happening in real time, we can get up on the phone, or we can get online and just ping these other observatories and say, hey, there's something awesome happening in this part of the sky. Point to it just as fast as you can. So we're really hoping that just with this kind of simple concept of taking photos of the sky every night will just unleash this world of opportunity to make quick, real-time discoveries. And I think it's going to be very exciting. So, what am I doing here? Long story short, why do they have observing specialists for a telescope that isn't actually complete yet? Well, there is an interesting thing. So due to the COVID restrictions, which is of course why I'm wearing this mask here, the construction of the telescope has been severely delayed. However, we have developed plenty of safety protocols so we can all keep working together and keep advancing on construction of the telescope and testing while being safe and considerate of our coworkers. So what I'm physically doing here, I'm in the kitchen of the Rubin observing facility, and next door to Rubin, we have a small 1.2 meter telescope, the auxiliary telescope, that's going to be used to run real-time calibrations of and atmospheric profiles of the same part of the sky where the Rubin, the main telescope, will be pointed. So what I'm doing here in this photo that I have in the slide is I'm observing with the 1.2 meter auxiliary telescope. It's going to serve as kind of a test bench for all of the softwares and all of the automating technology and AI that Rubin is eventually going to be using to make its decisions to observe at night. What I also hope to do as the first observing specialist is to implement a really impactful operations model and help design what this career will look like for future observing specialists, and how we can all make really big impacts at Rubin, and of course within the community for sure. And speaking of community impacts, I'd like to talk for a minute about something that's not related to cosmology, but is equally important, I'd say, is I am also a diversity advocate. So AURA, the Association of Universities for Research in Astronomy, is a nonprofit managing organization that manages the Rubin construction project. And I'm a diversity advocate for AURA. And what that means is I spend a lot of my time focusing on equity and inclusion in astronomy, not only in an academic sense, but I try to make positive impact on workplace culture in the various observatories that I've worked at, as well as working with the local communities in Chile and working with management at AURA to develop more inclusive operations models so that everyone who is currently working at the observatory is really being their best selves and able to contribute and is welcome and has a voice, and is that everyone can bring their true selves to work. This also has an outward facing model in that I want to focus on engaging the communities and engaging the future workforce to come in and really understand how exciting this career is and how important and meaningful these studies are. So here I just have a few pictures of things that we've done at the AURA facilities in Chile, which include the Rubin construction project, Gemini South Observatory, Cerro Tololo Inter-American Observatory, which is on the mountain peak, quote unquote, next door to us, and of course SOAR Observatory, which also shares the summit with Gemini South and Rubin observatories. So these have included things like discussing the science of the intersectionality of sciences and the arts, and discussing indigenous astronomy in Chile, and discussing women identifying employees at AURA, and just trying to understand how we can make astronomy, and how we can make observatories more welcoming places. So I hope that you've enjoyed this portion. I am going to stop sharing my screen and pass it over to our next speakers, Cyndia and Brad.
Thanks, Alysha. So I wanted to start off by talking a little bit about how we use instruments to study some of the questions that Joe was talking about, and in particular, the instruments that Brad and I use, which are primarily at the South Pole. So Joe mentioned the electromagnetic spectrum. So this is essentially all of the different kinds of light that we have. And you can think of light as a wave. So sometimes people talk about light waves. And the distance between the two peaks or two troughs of that wave, we call the wavelength. And light can come in all sorts of wavelengths. So you can have something like radio waves that you use to send signals over really long distances, like to your car or to the next city over. And those can have wavelengths on the order of kilometers. And you can have something all the way down to gamma rays, which are really, really small, and you have wavelengths that are the size of nuclei. And the visible light that you and I can see occupies a very, very small space in this spectrum, and it has wavelengths on the order of about the size of single-celled molecules, and everything else is still light, but is light in a form that you and I can't see. And an important thing about light is that everything emits light of some wavelength based on its temperature. So the sun, for example, is a few thousand degrees Celsius, and so its light is mostly peaking in the visible at around yellow. And that's actually like you and I, our eyes have evolved to be able to see visible light because that's where most of the sun's light comes from. Humans, on the other hand, are a little bit cooler, and our light is mostly peaking in what we call the infrared. So a little bit longer wavelengths than visible light. And so sometimes you hear people talking about like night vision goggles and being able to see people in the dark. And what those are essentially doing is they are able to see some infrared light, and so they are seeing people's body heat when they see people in infrared goggles. And so Joe mentioned that once upon a time, we think that the universe was really, really, really small and dense and hot. And you can kind of sort of think of it as like the sun, but everywhere. Like it was a plasma, it was really hot. It was so hot that like everything was on fire, but everywhere. And at some point, the universe started expanding. And as Joe mentioned, we're not entirely sure why this is the case. But as it expanded, it cooled off and cooled off and cooled off until at some point it wasn't this opaque plasma anymore. And over the course of the last 14 billion years, as it's been cooling off, the wavelength of the light it's emitting has been stretching out. And so we call this the leftover light from that Big Bang, the cosmic microwave background. And it's the oldest light in the universe, and it's currently at a very cool about 3 degrees above absolute zero, minus 270 degrees Celsius. And this is the oldest light we have left in the universe. And it is essentially a baby picture of everything that we have. And we try to look at it in order to understand some of the questions that Joe is getting at. Where did our universe come from? Why did it start expanding? Why does it look the way it does? So you might ask the question, that sounds awesome. Where do we go and measure the cosmic microwave background? And one of the key requirements is that you want a place with low atmosphere. So as the name implies, the cosmic microwave background is primarily in microwave frequencies. And it turns out that water in the atmosphere, water in clouds, in the sky absorbs microwaves. And this is actually the same way that your microwave oven works, is that it absorbs the microwaves in your microwave oven, and the water heats up, and that heats up your food. And And so if you would like to be able to see things beyond the sky, you want to be able to go to a place where there's not very much atmosphere. And so that necessarily means we like to observe from very high and very dry places. You want very few distractions, so things like radio signals, things like Wi-Fi, humans moving around generally all kind of mimic our signal, and so we want to avoid other people as much as possible in order to avoid things that might look like our signal that show up in the data that aren't actually coming from the sky. And another thing that might be important is good sky coverage. So what sorts of sky can you actually access? Are you actually looking at useful things? And I'll talk a little bit more about that in a sec. So one of the places that we've already talked about is Chile. So the Atacama Desert, where Alysha was calling in from, and where Joe talked about the Atacama Cosmology Telescope, is one of the premier sites in the world for studying the cosmic microwave background. It is extremely dry, and also incredibly high altitude, about 5,000 meters. And it has really great overlap with the optical surveys, such as the Rubin Observatory that Alysha was talking about. So you can imagine looking at a baby picture of the universe from the Atacama Desert and then overlapping that with a more recent picture of the universe that Rubin Observatory is taking. And so you can start to ask questions like, this baby picture we know has to evolve into this more recent picture. And so you can ask all sorts of questions about what sorts of dynamics allow that to happen. And so a lot of CMB instruments are based there in Chile. And then the other site that we use here on Earth is the site that Brad and I work at, which is the South Pole in Antarctica. So it turns out that Antarctica is the driest desert in the world, actually. And it's got the Antarctic plateau is about 3,000 meters above sea level. It actually feels a little bit higher because the effect of the Earth spinning around squishes out the atmosphere at the poles, so you actually get even less atmosphere than you'd expect for the altitude. And one of the really awesome things about observing from Antarctica is the sun only rises and sets once per year, and so you get a 6-month-long nighttime in which you have really, really stable and really clean observing conditions. One of the other things that I like about South Pole is that the US Antarctic program kindly provides 3 meals a day and runs a very nice trivia night. And so the South Pole telescope that Brad works on and the BICEP class of telescopes that I work on are all based here. So what kind of tools do we use to measure the cosmic microwave background? Unlike the Rubin Observatory, which is essentially a very, very large, very powerful camera, but the same sort of camera that you can buy when you buy a DSLR. We have to use special cameras to measure our microwaves because you can't just buy a microwave camera. And the way that I like to think about it is you're trying to measure a very, very cold 2.7 degree object. And the way we do that is essentially just with an extremely sensitive thermometer. So this is an image of the cosmic microwave background as seen by a satellite. So, you know, the ultimate in avoiding atmosphere is to go into space, but space is very expensive. So they took this picture, and you can think of light coming from the cosmic microwave background as being collected in some buckets that we have in our telescopes. And then we build very, very sensitive thermometers that we stick in the buckets, and we ask, how hot is the cosmic microwave background? How hot is the light coming from some direction? And then we move our telescope to another place. We collect more light in the bucket. We stick the thermometer in, and we say, how hot is it coming in this new direction? And by doing that a bunch of times, we can build up this picture of how hot the light is, and therefore this map of this baby picture of the universe. And so this is a field in which we've made enormous progress over the course of the last, honestly, couple of decades. So in the earlier part of this century, even the BICEP 1 telescope had about 50 of these light collecting buckets, and in the old days, they really did look more like buckets that it was using to make its maps. And SPT-3G, which is the latest generation of the South Pole Telescope series, was already 5 years old, which feels like forever in some technological advances. And they have 16,000 of these buckets, which are these very cool swirly patterns here. And that's actually why I got interested in working in this field. Is I didn't really have great opportunities to study physics. At my high school, we didn't really have physics classes, but I really liked the idea of building tools to study the universe, to try to figure out what nature was telling us. And so I got interested in building all sorts of tools that led me into studying how to build better detectors and better cameras in order to study the CMB. And that has given me lots of awesome opportunities. One of the coolest, I think, has been to travel to the South Pole to work on some of these experiments. And that's actually where I met Brad, who I will let take it away from here.
Thanks, Cyndia. So I'm going to share my screen here. So I'm going to tell you a little bit more about some of the experiments at the South Pole, and what they look like, and also just what it is, how it is like to work at the South Pole, since it's such a unique environment. And here you can sort of see what it looks like during the South Pole winter. In the distance here, you can see the experiments that Cyndia and I work on, the South Pole telescope and the BICEP experiments. So one of the first questions we often get is just, how do you get there? So how do you get to the South Pole anyway? And so this basically just shows the path. The first, you fly commercially to New Zealand, where the U.S. Arctic program is based. And from there, you take military flights, basically contracted through the U.S. Air Force or U.S. National Air Guard, to Antarctica. So it's still about an 8-hour flight from New Zealand to McMurdo on the typical flights we take. And then another 3-hour flight to the South Pole, which is at the center of the continent. Literally this SPT BICEP experiments that we work on are literally a kilometer away from the geographic South Pole at the bottom of the Earth. So this is the type of plane we take. This is an LC-130 plane, one of the main cargo planes for the U.S. Air Force, U.S. National Air Guard. The LC-130s are equipped with skis on them, so they can land on snow and ice. And as you can see on the right here, the amenities aren't very significant on the plane. You're basically sitting in cargo nets on the side of the plane with the cargo strapped down in the middle. Very loud, very long 8-hour flight, but it's the best way to get to the South Pole. Of course, along the way, you get some pretty amazing views on your way down there. You're flying over the Antarctic continent. The South Pole is about nearly 1,000 kilometers away from the coast. So you see all the Antarctic mountain ranges, glaciers, snow. Pretty unique view the whole way along this 3-hour flight to the South Pole. So when you get there, this is what you see. As Cyndia was also saying, you're at about 10,000 feet altitude. This is showing in the distance the welcome sign, but then on the distance, the station where there are beds for about 150 people at the South Pole Station, which sometimes gets up to during the summertime, which is, since they're in the Southern Hemisphere, it's summertime now at the South Pole. But this is a base where there are sort of several different experiments, atmospheric science, and astrophysical and studies of the cosmic microwave background going on there, which was Cyndia and I work on. So, roughly a kilometer away from the station is the so-called dark sector at the South Pole, where all our microwave telescopes are. You can see here the distance, SPT, and the BICEP experiments again. So typically every day when you're down there, you would walk a kilometer in the snow out to the telescope and back to the station to get your meals and ultimately sleep. And sometimes if you want to go fast, take a snowmobile on the way back. So when you get out to the telescope, one thing that's hard to appreciate is just how big it is. So this is showing some people at the base of the telescope, and here is the South Pole telescope. So it's a 10-meter diameter telescope, so it's about 30 feet diameter. It's a microwave telescope, so it's designed to observe these radio microwaves where this light from the Big Bang is the brightest. And the important thing about having a large diameter telescope is that a big telescope gives you fine angular resolution on the sky. You can see small features in the sky. So not only can we study features in this light from the Big Bang on small scales, but we can also start using it to study doing astronomy, seeing galaxies, seeing clusters of galaxies, seeing black holes, which I'll talk about. So, you know, this big telescope allows you to do a lot of different astronomy. And as Cyndia also mentioned, you know, one of the key features to do this science study in the light from the Big Bang is to develop the detectors and develop the instruments. And, you know, ultimately these features that we're going to be looking for in the cosmic microwave background, we're sort of looking at the distribution of matter in the very early universe, only a few 100,000 years after the Big Bang. And we're looking for variations in the distribution of that matter at this 1 part in a million level or even smaller. And so ultimately to see those fine variations in the distribution of matter and light in the very early universe, we have to make the detectors extremely sensitive. And to do that, we make them extremely cold, typically operating detectors roughly a fraction of a degree above absolute zero. And so a few years ago for SPT, we just deployed the new SPT 3G camera, sort of pictured, these are the detectors here. You know, we've assembled the focal plane for all the detectors in it. We're eventually going to, soon after this, we're going to install it into the camera to actually cool them down and take our measurements. And this is showing a picture of the team, part of the team that year that went down to help assemble and install the camera. So here's the team after we've installed the camera on the telescope, and now SPT is ready to observe. So it's going to just show a quick movie of what it looks like at the South Pole during the winter. This is a video that one of the winter overs down there for the BICEP Keck family of experiments made from a long duration exposure over several hours observing the South Pole. So it's on Vimeo. I definitely recommend checking out Robert Schwartz's videos. I'm going to scan through to get around some of the extra sounds just to give a sense of what the sky looks like there. So one thing unique at the South Pole that I don't know if we've mentioned yet is that since you are at the geographic South Pole during the summer time right now, the sun's up 24 hours a day, but come March, the sun is going to set and be below the horizon for 6 months where there's complete darkness. So when we leave people on the station and the South Pole Telescope and these experiments to run them, they're often isolated for 9 months during this austral winter to keep the station running and keep all these experiments running and taking data. So the winter time is some of our best observations. The air is really cold, very dry as the driest part of the season. And with the sun completely set, there's not as much turbulence in the atmosphere, which can cause problem for our measurements. And of course, since you're at the South Pole as well, you get all these southern lights that you can see prominently in a lot of these videos that come up. Just like the northern lights, there's southern lights associated with particles from the sun getting accelerated in the atmosphere and creating these fantastic light shows, which make a lot of great movies and images for winterovers down there. Photography is a pretty big habit. So just trying to some of the sort of emphasizing some of the science highlights, I guess, from some of the experiments down at the South Pole. I just wanted to bring a couple of things. So even though we're primarily looking at the cosmic microwave background, the SPT, it's part of this Event Horizon Telescope Network as well, which is this global network of telescopes that was trying to observe the event horizon of supermassive black holes in both the Milky Way and other nearby galaxies. And so a couple years ago, a big result came out, making the first picture shown here. This is the NSF director, France Cordova, holding that image, that sort of iconic image of this event horizon at the black hole of the nearby M87 galaxy to actually resolve this event horizon of the black hole in that galaxy 50 million light years away. So SPT is part of that network. You know, it's one thing that's unique about it. You know, these observations are done at the same wavelengths that we're doing these microwave observations, but as part of this global network, you can effectively create a virtual telescope the size of the Earth. And so a big telescope gives you fine angular resolution. So it allows you to resolve this event horizon in this unique way that SPT is taking part of. As Cyndia also mentioned, you know, described the BICEP heritage of experiments. So it's how big telescopes give you small angular resolution, fine angular resolution on the sky. So BICEP has a different strategy where they're trying to look at big features on the sky. So BICEP is our much smaller neighbor, but also famous in its own rights. But it has about a 0.5 meter diameter lens refractor. So it's about 20 times smaller telescope, but it's really trying to observe big features in these variations in the cosmic microwave background, this light from the Big Bang. And itself had a pretty headline-grabbing results several years ago of trying to measure the polarization of this light. So this, this is a map that they made of the polarization in the cosmic microwave background. So the sky, much like the sky is polarized, the light from the Big Bang is polarized, and we can use that to study conditions in the very early universe. And for the first time, this is showing a map. There's the moon for scale shown, map of basically roughly 3% of the sky of what these variations look like in the intensity of that light and the polarization patterns. And so these are sort of features that are at the roughly 1 part in a million, 1 part in 10 million level. But for the first time, they were able to detect this sort of curl pattern in these polarization signals, which we're hoping to use to constrain the conditions of the very early universe and ultimately learn about the physics behind the Big Bang. So it was an important milestone for BICEP to make this type of measurements of this polarization pattern in the sky, and sort of it's an important benchmark that they need to have more sensitivity, more detectors, much like we installed our 16,000 detector camera for the SBT 3G. They installed, the BICEP team installed their own significant camera. In the last several years, they've been upgrading. This is from a couple of years ago, or their latest edition, showing the team behind their own set of detectors, pictured at the center here, that are also going to be cooled down to a fraction of a degree above absolute zero. And then eventually installing this new BICEP array on one of their telescope mounts at the South Pole. So just to try to bring it together a little bit, I want to just have this last connecting thread here. So ultimately, though, just trying to connect some of the science themes we're doing of studying this, just trying to understand what we're observing when we're making this picture of the CMB. It's effectively this baby picture of the very early universe. This light represents what the universe looked like only a few 100,000 years after the Big Bang. And what's so powerful about it is it's a time in the universe before there were stars, before there were galaxies, where the universe hadn't had time enough to evolve the structure that we see today. But by comparing it to things like, the Rubin Observatory, what Alysha was talking about, the distribution of matter and galaxies in the universe today, is really getting very powerful bookends on the universe of what it looked like in the very first instance of the universe to what it looks like, in its sort of advanced ages today. And by comparing how they sort of two very different pictures of the universe, ultimately we're just trying to learn about how the universe evolved, the content of the universe, and because it's an extremely powerful lever arm to ultimately understand the universe, the content and physics of the universe, because it's, if you put it on a sort of a human equivalent time scale, it's this picture light from the Big Bang is only the first several minutes, of the human equivalent lifetime of what the universe looked like so long ago. So just wrapping up here, I think what's exciting about all this research, there's a lot of big questions that we're trying to answer. What physics was responsible for the Big Bang? As Joe was talking about, and Alysha, what is dark energy and dark matter, and trying to connect these very different pictures of the universe. And then ultimately, a lot of these observations also help us learn about black holes, general relativity, and physics of the extreme universe. So I think I'll end it there and hand it back to the moderators.
Thank you so much, everyone, for your contribution to this picture that you've created of what's going on around the research. We are delighted to bring to you live from the South Pole two of the researchers that are working there. We have with us Alexandra Sasha Rollin and Matthew Young. Can you hear us okay?
Yeah, we hear you guys loud and clear.
Wonderful, wonderful. So we understand that it's been an exciting day because you're getting ready for wintering over.
Yeah, we actually are. The last flight of the season just took off 5 minutes ago. We were all outside saying goodbye to all of our friends who were on that last flight and waving the plane off. So we're still warming up a little bit.
Cold fingers.
Yeah.
So how long will you be working there without a break or without being able to leave or having fresh faces come and visit you?
We're here until the end of October, so the next 10 months, 9 months. Yeah. Yeah, the people that flew out on this last flight will probably be the people that fly in on the first one 9 months from now. We got our last shipment of fresh food just a couple days ago, and we've got enough of that to last through a good chunk of the winter, and then after that we'll eagerly await the arrival of the first fresh fruits and vegetables at the end of October.
So now it's just 39 of us for the next many months.
Yeah.
That actually raises a question that was posed by our viewers as far as what are some of the difficulties that you experience individually or as a person when you are working in such an extreme environment? Things like sleeping and eating and just alone time.
Yeah.
Well, that's when you've only got 39 people, you all clearly rely on one another. So here at the station, we have maybe about 8 or so scientists running the telescopes and various experiments, but then we've got people like the cooks and all the people that facilities running, keep the power on, keep the heat on. All of that is absolutely essential, and so it's really important that everyone comes together as one cohesive group and can rely on every other person.
Yeah, we actually go through a pretty extensive, team building process before the station closes to kind of solidify that group effort. I would say probably the most difficult thing here is just the remoteness and having to deal with that psychologically. We only have good internet access a couple hours a day, and so it's a little hard to communicate with people back home. You're kind of removed from the news of the world a bit, which might have its ups and downs. But yeah, we kind of learn to rely on each other and get through it together.
Like you said, in terms of sleeping as well. So currently we have 24-hour daylight. So as you can imagine, it can be tricky to sleep when the sun is up 24 hours a day. Mm-hmm. And in just over a month, the sun will start to dip down below the horizon, where we'll have a couple of weeks of twilight and then roughly 6 months of darkness. And so apparently that is tricky to get your own body clock running with 24 hours of darkness as well.
Yeah, but with the darkness comes the really beautiful night skies. We've seen lots of photos of them. Neither Matt nor I have wintered here before, but there's you can see all the stars, and there's really great auroras that appear through most of the nighttime. And then the sun rises in September. Yeah, it's a big celebration at the end of winter. And we usually have kind of big events for sunrise, sunset, sunrise, and midwinter are kind of the big winter holidays that we have here to mark the occasions. Yep.
A related question that's been posed, and I think this is applied to all of our speakers. How has your work changed because of the pandemic and because of COVID?
So the work at the South Pole, actually, they try the NRD program tries to maintain continuity with the major science programs, and SPT is one of the big ones. So we were able to kind of relieve the last year's winter overs, and Matt and I came in and took over for them for this coming year. But usually in the summer season, right now, we would have a whole team of people here doing a bunch of maintenance work and upgrades and things, and we didn't get to do any of that this season. Fortunately, SPT is in a position where we're sort of doing continuous observing, and we didn't have any major changes planned for this season, but other projects had to scale back quite a bit and hold off on finishing or following through on their plans for upgrades and major work that they had planned for this season. So hopefully that can continue next year. we'll see, I guess, how the pandemic plays out.
Yeah, well, as you can imagine, it's tricky to get to the South Pole, even at the best of times. It can take, usually around a week to transit from, say, North America to here. But especially with this year and everyone doing their best to try and keep COVID off of the continent of Antarctica, there was lots of quarantine steps along the way. And so I think it took us about a month and a half from leaving North America to finally arriving at the South Pole this year. So very, very long delays to get everyone and everything down.
Yeah, and the main goal for this season was to keep COVID off the continent, and we appear to have succeeded, at least on the American stations. So that's great.
Congratulations. 6 weeks to get to your location. That's amazing. I do have one more question, and that is, what will your day look like tomorrow when you get up?
What's on the schedule?
Well, actually, slightly related to that is not quite tomorrow, but on Saturday, everyone will be sitting down and watching The Thing, the film. All 3 versions. It's a tradition here at the South Pole where when station closes for the summer and the winter season starts, everyone will sit down and watch The Thing. So we're all looking forward to that.
Yeah, that'll be really fun. Yeah, I guess our typical workday revolves around maintaining the telescope. So we have daily schedules that we maintain, and we have to recycle the cryogenic system, make sure that everything is up and running. So we usually start the morning by checking on those schedules and starting a fresh cycle. We'll go out to the telescope to do daily rounds. So make sure all the motors are functioning properly, make sure all the data are coming in correctly. No faults in the electronics, things like that. We also have weekly or bi-weekly greasing tasks. So got to make sure everything is well oiled and greased and running smoothly. There's a dog in the background.
I'm sorry.
That's all right. We miss animals here. That's sort of the gist of it. We will probably have some analysis tasks that we get up and running here, and some side projects that we'll work on, helping around at the station with various tasks, things like that. Lots of social activities to keep everybody busy in the evenings. So, yep.
Oh, well, you heard my dog bark. So does that mean you can't have pets?
No pets.
No.
Yeah, we can have photos and videos of pets, but no live ones.
Okay.
We do have a greenhouse though, so we have some fresh vegetables throughout the winter. So it's a little bit of a taste of home, I guess. Yeah.
Probably don't appreciate what it's like until you can't have it when you want it. Oh, Matt,
Yeah.
Sasha, thank you so much for joining us. I know it's been a really busy day for you. And we're just very delighted that you were able to join us and give us a glimpse into what's happening. And I think throughout the whole program, it's been amazing. Your views, your night sky can just be amazing when the sun sets. So thank you. I hope you have a really productive winter over. 10 months. Bless your hearts.
Thank you.
Thank you very much.
Thanks for having us.
We would like to take a few minutes to ask questions of the other speakers. And one of the questions that was posed was, why would the magnetic field not disturb observations in the South Pole? I'm not sure who to pose that to.
I can take a stab at it. I mean,
thank you.
I think I mean, for the most part, we're trying to do these millimeter wavelength microwave observations of the sky. So even actually when the sky is blue, when the sun's up in the summer, effectively the sky is still extremely transparent. So if your eyes were microwave sensitive, you would just see this sort of night sky afire with this light from the cosmic microwave background. So I mean, the magnetic field, the only way it affects us really is through, it can actually affect the instrumentation at some level. Like we are trying to do some of the cryogenic sub-Kelvin detector technology that we use can have some sensitivity to magnetic fields, but it's also just on a scale and at a level that really doesn't affect our measurements. And we do have shield it in some way just to make sure that it doesn't affect us at all.
Okay, so you can account for it when it is present.
Yeah, and it's mainly the Earth's magnetic field is sort of something that's sort of pretty static and affects things at a very large scale. So it's not something that's varying on the sky like the signals that we're looking for from the cosmic microwave background.
Okay, another question that we had was, can you explain the Einstein space-time curvature or give that a little context? The Einstein space-time curvature.
Shall I jump in?
Yeah.
Sure, Joe.
Great.
Yeah. Well, so there's this big question of like whether space. We asked this question about whether space is flat or curved, which is kind of a weird question, right? Because you think of space as just the, it's the space you're in, right? But it turns out that depending on how much space weighs on average, like the mass of stuff in space actually can distort space a bit. Like imagine taking a big rubber sheet and putting a big lead ball on it. It deforms it. But if you put something less heavy on it, like a foam ball or something polystyrene, it won't bend it very much. And so I actually think Einstein kind of taught us that any mass in space actually distorts the space, a bit like putting a weight on a rubber sheet. And one of our big questions is, how much on average does the stuff in space weigh? Does it distort it so much that space itself gets on average so distorted that if you shoot a straight ray of light through it, or shoot two beams of light through, they wouldn't in the end travel in straight lines. They'd in fact in the end curve towards each other, a bit like the sort of concept of space then, rather than being space being flat, it would be curved like the surface of an orange or something. Now right now we seem to, all our observations, and actually many of those have come from the cosmic microwave background, from satellites in space, and now with our telescopes on the ground in Chile and the South Pole, it does seem to be that the weight of space on average is such that it is flat, which means that light travels in straight lines, and that we think space kind of stretches on out forever in all directions. But it's something that we're actually really trying to measure. It was one of the measurements we made a measurement of that just recently with our telescope in Chile, because there was this curiosity that maybe it wasn't completely spatially flat, but it does really seem to be on average light travels in straight lines, space seems to just stretch out forever. But it's a very interesting question.
Well, in a follow-up to that, Joe, what is the difference between dark matter and dark energy? Is there a difference?
Question. Yes, they are different, but we are very unimaginative as physicists, and so we've given them very similar names, which really confuses. So dark matter is the name we give to invisible mass that seems to surround us and surrounds our galaxies, and we think is just a new kind of particle. Probably, we're not completely sure. But and so it kind of behaves, gravity pulls it together, but doesn't emit any light. So it's basically invisible matter. Dark energy is weirder. It seems to be our best guess right now is it might be the energy of empty space itself. You take a box of space with nothing in it, but actually it seems to might have its own energy. And Einstein himself said that this was a possibility, that maybe space could have its own energy. And actually, as space grows and grows, you actually get more and more of it. And it seems to be making the universe speed up. So that's the dark energy bit, and it's weirder, we think, than the dark matter.
Oh, thank you so much. And Frank, thank you for that question. I might have been guilty of conflating the two before, so thank you. Alysha, this question is specifically for you, I believe, in regard to mentioning that it's going to take 10 years to build the telescope. Why does it take so long?
Well, so that was a misconception. The telescope survey, so it will be running, taking the pictures. That is the process that will take 10 years. So its dedicated purpose is to take photos of the southern hemisphere continuously for 10 years. Now, this telescope actually broke ground in April of 2015. And we are in, so 6 years. The telescope above me, it's actually physically above me, is still in pieces, but the mirror, the giant mirror, has already been cast. Many of the pieces are just here waiting for specialists to come in and assemble them. And it's being developed by a lot of different entities. It's being developed by many different working parts. So people to build the dome, there are specialists who come from Italy. There are people working on the camera at the Stanford National Acceleration Laboratory, or SLAC, and they are in charge of building the camera. We have specialists who come in to work on the telescope assembly, the truss system, or the, let's call it the housing that will keep the mirror in its place, will support it, and will allow it to rotate about the sky and to point in altitude from very low places, just almost pointing directly at the horizon, to pointing directly overhead. So we hope, I mean, at this point, I could say probably in 2 years, all of these working pieces will be in at least one place and will be very closely, they'll be very close to being assembled. And I guess in 2 years, yeah, well, it will have been under construction for 7 to 8 years. It's just incredibly complex systems while being also simultaneously incredibly delicate. And as I came up to the summit for my observing shift today, we have there was a delivery of a crane that can lift 500 tons. Now this crane is going to be assembled so it can lift the mirror in its entirety out of the telescope, put it in an elevator, and then put it into a special cleaning room where the reflective material will be restripped and repolished or reapplied once every 3 to 5 years. Now, just to deliver that one piece of the observatory has taken months. And the trucks were parked at the very bottom of the observatory road. It took them 4 hours to travel 30 kilometers to bring these pieces and leave them at the doorstep. So that's just one facet of why it takes so long.
Quite a bit of collaboration there. And
Absolutely.
Speaking of collaboration, there was a question posed in relationship to the closure of the program in Puerto Rico and whether or not that has affected the community's work in mapping the universe.
But Brad,
No?
I can say something, but do you want to? I can say one.
Yeah, you start, Joe. You start.
So I don't use it. This is the Arecibo telescope in Puerto Rico. It's like a magnificent telescope. It's not something that I or my collaborators use directly. But one of the things where it sort of touches on things that we're all trying to do. So one of the things that many of us are trying to do in Chile and the South Pole are detect gravitational waves, ripples in space-time that we think were put in at the Big Bang itself, like space-time rippled at the Big Bang and produced gravitational waves. We think we're looking for them. One of the neat things that Arecibo was doing, amongst many other things, was tracking these very rapidly spinning stars called pulsars, where they spin so rapidly and so regularly that you can actually time them and look for other kinds of gravitational waves rippling through space that could be coming from black holes colliding, from galaxies merging together. So for me personally, that's one of the things I'm sort of really excited about looking for, about other people telling me about, other scientists, is that they've seen these gravitational waves from colliding black holes. But Arecibo was definitely one of the was a really key part of tracking these, like timing these spinning pulsar stars to look for them. They'll still be able to keep looking for this, but for me, that was one of the things that I, really noticed amongst many of the other science areas. But
yeah, and Arecibo is a radio telescope too, so it's at wavelengths even longer than the ones that we're looking at for the South Pole telescope or the Atacama Cosmology Telescope in Chile. So it's factors of 100 longer wavelength. Looking back to sort of Cyndia's plot of the spectrum of light. So like the radio signals that they were looking for were from a lot of it. I mean, there's a lot of science that it was doing, in terms of these pulsars, just studying the gravity waves from them, even solar system science, many things, but it wasn't contributed in this area for looking at event horizons, black holes in the Milky Way or whatever, or the studies of the cosmic microwave background so much. But it was doing a lot of different studies of the universe and that wavelength range.
Thank you. Thank you so much. We have other questions, but unfortunately we're running out of time and we need to wrap things up for the evening. How exciting. If you are interested in evaluating our session, please go to c2st.cnf.io and share your feedback, all your agreements, your suggestions. We want to continue to offer programs of this nature. And thank you so much to you, Joe and Alysha and Cyndia and Brad and Sasha and Matt, for your valuable time and your expertise and for helping us put together this amazing program. If you like what you saw and you are interested in donating, you can do so at c2st.org. You can also learn more about our future programs. And we will be having a program next Tuesday with the Shed Aquarium and researchers there. So we would be happy to have you join us again. Thank you and have a good evening.